Okay, we're now going to begin our discussion on complex numbers. Complex numbers bother people at first, but they're actually very useful. I'll talk about some of those uses later on in the next video. So let's just dive in here like we normally do. And we're going to start with a simple quadratic equation, x squared plus 1 equals 0. Now, if I just try to solve this by saying x squared is equal to negative 1, and then x is equal to plus or minus the square root of negative 1. Now, we know that we can't do a square root of negative 1 in the sense that it's not a real number, but this is where this idea of complex numbers come in. What we have here is we define I as the imaginary number, and so and we define I as equaling the square root of negative 1. So x equals plus or minus the square root of negative 1 is the same thing as saying x is equal to plus or minus I. Now, if you've never seen imaginary numbers before, it kind of looks a little weird, and some of you might say, well, if they're imaginary, why are we bothering studying them? And the reality is imaginary numbers have a bad name for them, and the story I think is kind of interesting or funny how they got their name. This was several hundred years ago. Mathematicians were looking at solving quadratic equations, and people didn't always feel comfortable with some of these more abstract concepts with numbers. And what I mean by that is some people didn't even believe in negative numbers, meaning that they didn't like the fact that x could be -3, for instance. They're like, no, that doesn't make sense. You can't have negative numbers. And there was also some people though that were studying it and saying, they really were bothered by the fact that not all quadratic equations had solutions. And so some of them, had this kind of imaginary number. They're saying, okay, well now all quadratic equations have solutions. We can get two solutions for our quadratic equations. And then another mathematician, or a couple other mathematicians, wrote some papers and published them, and basically kind of criticizing these mathematicians who were using this concept of the square root of negative 1, and basically as a derogatory term said, well, if you use these mathematicians' negative numbers, you get solutions, but we know those don't even exist because they're imaginary numbers. If we use their imaginary numbers, they'll get solutions. And well, the term kind of stuck. But I want to emphasize imaginary numbers are no more imaginary than negative numbers, or for that matter, even something like pi. And the reason I say negative numbers, just right now, sit and think about displaying -1 pencils. And you can't. Some of you might say, well, -1 pencil means I owe you a pencil. And my response to that be, that's an interpretation of what a negative number can mean, but it's not an actual displaying the quantity of -1. And the same thing is true when we talk about even things like pi. Display exactly pi ounces of flour. Well, we can't do that because pi is an irrational number that goes on forever and doesn't have decimals that repeat. So it's impossible for us to do that. And so this concept of imaginary numbers, an unfortunate name, but it's still a very powerful tool for us. And as I said, I'll talk about that application in the video, the next video. Alright, so let's talk about some ideas here with I. And let's first do just how we can do powers of I. So we know that I is the square root of -1. So then what is I squared? Well, I squared, of course, would be I times I, which is the square root of -1 times the square root of -1. So that's just -1. I cubed is I times I squared. So that would just be I times -1, which would be -I. I to the fourth is simply I squared times I squared, which is -1 times -1, which of course -1 times -1 is just +1. And we can keep going, but as soon as we hit I to the fifth, we would have I times I to the fourth, and we would get just I times 1, which is I. So we actually get this, what's called a cyclical, it's a pattern. And to kind of illustrate that, I'll just go over here and say, well, we have I is equal to, of course, just I squared is equal to negative 1, I cubed is equal to negative I to the 4th is equal to 1, I to the 5th is equal to I to the 6th is equal to negative 1, I to the 7th is equal to negative I to the 8th is equal to 1, and then we could just keep going on forever, doing more positive integer powers of I. Alright, so we have that. Now, the next thing we want to talk about is complex numbers in general. And so complex numbers, sometimes you'll see them, and I'm going to do this often, is we write z sometimes to refer to a complex number. Z equals a plus bi. This is a complex number, and it has what's called a real part, a, and then imaginary part. Now, when we talk about the imaginary part, we don't include the I, we just include the letter in front of it, which is B in this case. And so sometimes you'll see us abbreviate real part as RE and imaginary part as IM. So just as a quick example to illustrate this, if we have Z is equal to 3 plus 2I, the real part is equal to 3, and the imaginary part equals 2. Now, I'm not going to spend a lot of time on this. The next thing here is when our complex numbers are equal to each other, and that's when the real part and the imaginary part are both equal to each other. So let's talk about adding and subtracting imaginary numbers here, or complex numbers. It's actually pretty straightforward to do. Adding, subtracting, multiplying, and dividing. Dividing is the only one that's a tiny bit tricky. It's not hard, it's just a little bit more that we have to be careful with. So if we want to add two complex numbers, so if we're doing the sum, you'd have a plus bi, for instance, and then plus c plus di. And what's nice is this is really just, you can think of it as combining like terms. You would have a plus b, not a plus b, a plus c. If I can erase, come on, erase, there we go. A plus c plus the quantity b plus d times I. And as I said, it's really just combining like terms. And so if we do the difference, it's very much the same way. You have a plus bi minus, now notice that we still are doing the minus with the parenthesis here, because you would distribute that negative, but it is still just combining like terms, so you'd have a minus c plus b minus d times I. So let's look at a couple quick examples here. So suppose we have 3 plus 4i plus negative 2 plus 5i. Now we want to add these together, and so we just combine like terms. And so combining like terms, you'd have 3 plus negative 2 plus 4 plus 5i, and it's not necessary to write this step down that I just did, but then 3 plus negative 2, of course, is just 1, and then 4 plus 5 is 9, and so I would have 9i. Okay, so as I said, hopefully pretty straightforward. Alright, let's do a difference one. Not really too much else going on in this one. So let's do negative 2 plus 3i minus negative 4 plus 4i. So again, we're just going to combine like terms here. So I'd have negative 2 minus a negative 4 plus a 3 minus 4i. And then negative 2 minus negative 4, of course, would be 2 plus 4, so this would be 2. And then 3 minus 4 is negative 1, so I'd have minus 1i, which, remember, we don't typically write a 1, so it'd just be 2 minus I. Alright, now let's talk about multiplying here. Multiplying is actually also pretty straightforward. Multiplying complex numbers, you just FOIL out and simplify. Or if you don't need to FOIL, you just distribute. And what I mean distribute is if there's just a single number in front of the parenthesis. So let's look at two quick examples here. So let's look at 2i times 3 plus 5i. So this we'd just do a normal distribution. So we would take this 2i, we'd multiply it into the 3 and into the 5i. And so we'd have 2 times 3, which of course is 6i, and then 2 times 5 is 10, and then I times I is I squared. But this is where we need to simplify, because we know that I squared, if we go back up to that list we had at the beginning of this video, I squared is equal to negative 1. So this would be 6i minus 10. Now we typically write these with the real part first, so negative 10 plus 6i. But really just multiplying out and simplifying. Let's look at one here that we've got, which is 3 minus 2i times 7 plus 2i. Now again, we just need to FOIL this out and then simplify. So FOILing it out, the first would be 21, the outside would be plus 6i, the inside would be minus 14i, and then the last would be minus 4i squared. So this would be 21, 6 minus 14 is minus 8i, minus 4 times negative 1, because I squared is negative 1. And then finally simplifying that, minus 4 times negative 1 would be plus 4. So 21 plus 4 is 25, minus 8i. Alright, now before we move on to division, we want to talk about something called complex conjugates. Now complex conjugates is very similar to just regular conjugates. And so if we have a number, z equals a plus bi, its complex conjugate is a minus bi. And so a real quick example here is if we had 3 plus 2i, the complex conjugate would be 3 minus 2i. Now the complex conjugate has a very special property when you multiply them, because if you look at this, we have 3 plus 2i times 3 minus 2i. Now you could FOIL this out, but remember this is basically having a plus b times a minus b. So it's the first term squared, so we'd have 3 squared minus the second term squared, which is 2i squared. So this would be 9 minus 4i squared, which would be 9 minus 4 times negative 1, which would be 13. Now what is special about multiplying complex conjugates is notice that we don't get any more imaginary. We get a real number as an answer. That will always be true if you multiply complex conjugates. Alright, so to wrap up this video here, we're going to do some examples of dividing. Now the first one we're going to do is what I consider a relatively straightforward dividing. It turns out when doing division of complex numbers, we're actually never going to actually do division. It's going to be multiplying. It's not like the same as rationalizing denominators, but we're going to essentially kind of do some of that idea there. Alright, so let's look at a quick example here. So we have 3 minus 5i divided by I. Now when you have just a single imaginary number in the denominator like this, as opposed to a complex number, we can just simply, to evaluate what this is use the fact that we know that I squared is negative 1. So if I multiply the denominator by I, I'd have I squared in the denominator, which is negative 1. But if I multiply my denominator by that, I have to also multiply the numerator by that. And so if I do that, well, you'd get 3i minus 5i squared over I squared, and then we simplify. So this would be 3i minus 5 times negative 1 over negative 1, which would be 5 plus 3i over negative 1, and then we simply finish out by dividing by that negative 1, and we'd have negative 5 minus 3i. So we didn't really do any division there. I mean, I guess tiny bit at the end. We divided by negative 1, but it was mostly multiplying and simplifying. Now, when we have two complex numbers, so they have both a real and an imaginary part, the division is, again, not going to be division. So we have 2 plus 3i divided by 4 minus I. Now, I can't just multiply by I like I did in the previous one, but this is where this complex conjugate goes in. If I'm trying to get just a real number in the denominator, if I multiply the denominator by the complex conjugate, we know that that's got that special property of complex conjugates multiplying, always giving me a real number. Well, if I do it in the denominator, I of course have to do it in the numerator as well. And so now I have to FOIL these out and simplify. So the numerator would be 8 plus 2i plus 12i plus 3i squared. Don't know why that little box went around my 12i. Okay, there it's gone. And this would all be divided by, now remember, we're doing complex conjugates multiplied, so we can use that special formula of a minus b times a plus b. So this would be 4 squared minus I squared. So combining some terms here, we'd have 8 plus 14i plus 3 times negative 1 all over 4 minus negative 1. And so doing this, we'd have this equaling to 5 plus 14i sorry, I lost my train of thought here. 5 plus 14i, because 8 minus 3 is 5, over 4 squared. That's where my mistake was. Something's not right here. I said 4 squared is 4. 4 squared is 16. So we'd have 5 plus 14i over 17. Alright, sorry about that mistake, but we caught it and fixed it. And so we could write this then as, oh, I'm sorry, I got my train of thought. I also forgot. No, we're good. I thought I was wrong, but we're good here. Mine's going off on tangent here. 5 over 17 plus 14 over 17i. So let's do another one, since I kind of got a little sidetracked there on that example. Let's do one more here of multiplying. Make sure, and I promise I won't mess up on this one here. So let's look at 6 minus 7i divided by 1 minus 2i. So again, what we're going to want to do is multiply by my complex conjugate. So the complex conjugate would be 1 plus 2i divided by 1 plus 2i. So then we FOIL out the numerator. So we'd have 6 plus 12i minus 7i minus 14i squared. And then the denominator would of course be 1 squared minus 2i quantity squared. So this would be 6 plus 12 minus 7 would be 5i minus 14i squared, and the denominator would be 1 minus 4i squared. So then we'll simplify. 6 plus 5i minus 14 times negative 1 all over 1 minus 4 times negative 1, which would give me 16 plus 14, which is 20, plus 5i over 5. And then dividing those out, you'd get 4 plus I. So again, we really don't do much division here when we're actually dividing complex numbers. Whoa, came back here. Let's just, oh, it doesn't like the fact that it wasn't syncing. That's fine, whatever. So when we're doing division here, again, we're actually doing more multiplication and simplifying than we are on it. Now, some calculators do have complex numbers on them, and they can do complex numbers. In the next video, we'll actually look at some examples of, well, an application of it, and then also seeing this as a solution to a quadratic equation.